Hey, hello, welcome back. This is Calculus 2 and finishing off Chapter 9 with hyperbolic functions. And you can study hyperbolics just like you study the trig functions. They behave extremely similarly with regards to derivatives and certain basic identities. So we begin with the definitions. They're actually exponential functions. So compositions, or maybe I guess we could think of them as sums and differences and quotients of exponentials. So sinh is going to be defined as e to the x minus e to the negative x all over 2. Cosh, hyperbolic cosine, is going to be e to the x plus e to the negative x over 2. Hyperbolic tangent, or tanh, is going to be 2. Sorry, I'm already thinking ahead. It's just the ratio of sinh and cosh, believe it or not. So just like tan is the ratio of sine and cosine, tanh is the ratio of sinh and cosh. So when all is said and done, this will be e to the x minus e to the negative x all over e to the x plus e to the negative x. Okay, and then we can get the other basic hyperbolic sort of identities just using these three, right? So cosh, hyperbolic cosecant, lost a c there, is really just 1 all over sinh, right? So this will be 2 all over e to the x minus e to the negative x. Hyperbolic cosecant, or sech, is just going to be 1 over cosh. So that will be 2 all over e to the x plus e to the negative x. And then, of course, hyperbolic cotangent, or coth, is just going to be cosh over sinh, or 1 over tanh. They just say the reciprocal of tanh, so that would be e to the x plus e to the negative x over e to the x minus e to the negative x. Okay, so it's new, but it's not too difficult to kind of get your brain wrapped around what's going on. Evaluating these things, then, sort of the first question that's on the chopping block for these problems in the homework. It's just a matter of using these definitions. So odds are you won't have Cosh button on your calculator, right? You may have one in the menu somewhere, who knows. So how do you evaluate cosh of 0? Well, you're just going to plug it in for x, right? E to the 0 plus e to the negative 0 is just e to the 0 again, all over 2. E to the 0 is 1. So 1 plus 1 is 2, all over 2, which of course is 1. So pretty simple, right? You could do anything else. So another example, maybe tanh of 1. So we'll have e to the 1 minus e to the negative 1 all over e to the 1 plus e to the negative 1. We can rewrite that as e minus 1 over e all over e plus 1 over e. And we hate complex fractions here in math education land. So we're going to multiply by e in top and bottom, so get e squared minus 1 all over e squared plus 1. Okay, so good fun. Of course, then you would put it in your calculator and get an approximation. Okay. Another thing then, once you get this, of course, you could always figure out the graphs by doing a sort of a plotting table plot. So for example, if I wanted to graph cosh, let's take a look at that example. You could, again, go back to the original identities, e to the x plus e to the negative x over 2. And maybe a little easier to rewrite that by butterflying it. 1/2 e to the x plus 1/2 e to the negative x. These two functions alone, we should know how to graph those from our pre-calculus class. So 1/2 e to the x is going to go through 1/2. So let's put 1/2 here. And put 1 here. And it's an exponential growth function, right? So it's going to go up like that. And of course it has an asymptote as x goes to negative infinity. 1/2 e to the negative x is exponential decay, so it's going to look like this. And then Cosh is the sum of the y components at each x value, right? So as you go further to the left, because the y values on the exponential growth function are getting smaller and smaller and closer to 0, as we go to negative infinity, the graph is going to get really, really close to the exponential decay. And then in the middle here, adding them together, you get this y value plus this y value, and then culminating at 0, 1/2 plus 1/2 is 1, and then going away, it'll sort of gravitate towards the exponential growth part of the graph. So what you end up with is this parabola-looking thing. It's not a parabola. It looks like one, right? If you ever see the St. Louis Arch, right, that thing is not a parabola. It's actually I think it's an inverse hyperbolic, or maybe it is negative Cosh. Okay, maybe it's some sort of negative Cosh. I don't know. You have to look it up online. Okay, the St. Louis Arch. So you can do a little bit of history, or I don't know what that would be, architecture maybe, for today. And you know, it's not a parabola. So a parabola would go up much slower. Okay, this just has exponential growth as it goes up, so it's definitely different. Anyways, all the graphs are in the book. I'm not going to beat you up over it. Let's look at maybe some identities. So like I said, these behave a lot like trig functions, and you could have a whole class in doing hyperbolics. It's not used as much. Okay, that's the reason why we don't really see it. So the most important identity, just like cosine squared plus sine squared equals 1. So I hope you have that memorized from trig. The most important identity here is cosh squared x minus sinh squared x equals 1. And you'll want to verify that. Obviously, if I was doing my written test, I would have to see it. I think in the homework, though, you're not really having to do much of anything. Let's go ahead and get in. Let's make this the quiz. This is the third quiz. Okay, so you have to prove that cosh squared minus sinh squared is equal to 1 for 5.9. Let's just put in 1. Prove cosh squared x minus, and I want you to do the proof just like I'm going to do here. So I want you to basically copy it. Okay, so starting on the more complicated side, which is the right-hand side, I note. And the goal is to go from the left to the right, or the right to the left, or kind of do a channel idea where the French are coming in from the right and the British are coming in from the left. Some sort of variation on that theme. Traditionally, we start on the more complicated side, so in this case, cosh squared x minus sinh squared x, and then we use algebra to get to 1, right? So we can rewrite these using the original definitions. Squared minus, and I'm going to have to FOIL that top part out. Okay, so e to the x plus e to the negative x squared is the same as e to the x times e to the negative x times e to the x plus e to the negative x all over 4 minus this thing squared. And then we have the FOIL, so e to the x times e to the x. Remember the rules for exponents. If you have like bases, so a to the x times a to the x up here at the upper right, that's equal to a to the x plus x. In other words, a to the 2x. It's not a to the x squared. Okay? You add the exponents. So here we'll have e to the 2x plus e to the negative x times e to the x. E to the negative x times e to the x is what? Well, you add the exponents, and then that will be e to the 0, which is just 1. Okay, so we'll have plus 1 for the outer, and then the inner will again be plus 1, and then the last plus e to the negative 2x minus, this time we'll have e to the 2x minus 1 because of the negative, and then plus e to the negative 2x. Okay. We could simplify and combine over the common denominator. 2 plus e to the negative 2x. You've got to make sure you distribute the negative to that second numerator. Okay. E to the 2x's cancel. Negative e to the negative 2x cancels with the e to the negative 2x. And then 2 plus 2 is 4. And then 1, which is the right-hand side. I started on the left, right? Whoops, I'm so sorry. I don't know my left from my right. The left-hand side. And then we ended, which is the right-hand side, which is what we wanted to show. Okay. So that would be your third quiz. You just have to copy that out, or hopefully do it from memory. And okay, so identities, same sort of identities as for the proving trig identities, same sort of idea. Okay, so section 4, now finally getting the calculus. First we'll deal with derivatives, and then integration, differentiation, and integration. Okay, so again, we can pull this off. If you didn't know how to do the derivative at all, you could prove the derivatives by kind of, again, defaulting to the exponential interpretation. So Cosh is the same as e to the x plus e to the negative x over 2. Let's rewrite that, right? So we want the derivative of 1/2 e to the x plus 1/2 e to the negative x. Okay. The first derivative, leave the 1/2 alone. The derivative of e to the x is e to the x. And then the second derivative, leave the 1/2 alone. The derivative of e to the negative x is e to the negative x, right back at you, times the derivative of the exponent. The derivative of negative x is -1. Okay, so we could rewrite this as 1/2 e to the x minus 1/2 e to the negative x. Okay. Of course, you could rewrite that, again, noting, what do we have here? E to the x over 2 minus e to the negative. You have a common denominator, and you just combine the numerators over the common denominator, and lo and behold, what is that? Well, that's sinh. Cosh gives you sinh. So the derivatives work a lot like the trigonomic derivatives, except the signs are off. Because remember, the derivative of cosine is not sine, right? The derivative with respect to x of cosine x is actually equal to negative sine x. So it's similar, but the signs are different. So that's really the only thing you have to memorize, and I do expect that you have these derivatives memorized. The only difference is, of course, the signs are different. So the derivative of sinh is Cosh. The derivative of Cosh, believe it or not, is sinh. And the derivative of tanh is going to be hyperbolic secant squared. The derivative, and then the rest of them are negative. Okay, that's kind of how I remember it. These first basic ones are positive, and then on the other side they're all negative. Okay, so hyperbolic cosecant or cosec is negative hyperbolic cosecant, hyperbolic cotangent of x, and then the derivative with respect to x of hyperbolic secant or sec is negative hyperbolic secant times hyperbolic tangent. And then finally, the derivative of hyperbolic cotangent, or cosh, is negative hyperbolic cosecant squared x. Okay. And then, of course, if you know these derivatives, you get for free a whole bunch of integrals. So the integral of, cosh x dx gives you sinh x plus c. The integral, of course, of hyperbolic secant x, hyperbolic tan x dx is negative hyperbolic secant x plus c. So if you know it one way, you should know it the other way, just like with the trig function. So I'm not going to write them all out for the sake of my own sanity. Okay. So let's take a look at doing some derivatives and integrals. Let me skip into my chapter here. Okay, so let's look at number 22, the old number 22 from my book. We'll just call it an example. Y equals hyperbolic tangent. Let me change it from what the book says, 5x squared minus 3. Okay, so chain rule is in order. So y prime derivative of hyperbolic tangent is hyperbolic secant. Hyperbolic secant of 5x squared minus 3. And then the chain rule, you have to take the derivative of the guts, the 5x squared minus 3. So that will be 10x. So at the end of the day, the derivative, rewriting it nicely, 10x hyperbolic secant of 5x squared minus 3. Okay. Let's look at some more examples. Let's get another example. Okay, so g of x equals the natural log of cosh of x cubed. So this is one where we have multiply nested composition. What you usually do is go with the parts, right, and then rewrite it. So the innermost part I'll call u is x cubed. And then the next level out, I'll call v is cosh of u. And then the next level out, I'll just say is the g of x, or yeah, g of what'll be v. Let's just call it y for the sake of simplicity. Will be the ln of v. Okay. So to get the derivative, what you're going to do is just basically take the derivative of the parts and multiply them together. So the derivative g prime of x is the derivative of y. So that'll be 1 over v times the derivative of cosh, which is sinh, times the derivative of u, which is x cubed, right? So 3x squared. And then you have to put it back in terms of x. So g prime of x, one thing at a time. V is cosh, sinh u, 3x squared. And then we could back substitute for u. So we would have cosh of x cubed times sinh of x cubed times 3x squared. And then you could use your identities, which are in the book. There's all kinds of identities listed in the book to simplify this. This identity we already know. Sinh over cosh is going to give us tant. Right. So we'll end up with 3x squared hyperbolic tangent of x cubed at the end of the day. Okay. Okie dokie. So yeah, these can be kind of challenging. Let's look at some integrals, right? Okay, so let's take a look at something like the integral of hyperbolic sine of 2 minus 5x dx. Okay. You probably want to do a u sub. There's going to be a constant of -1/5 floating about. If you want to equalize it, you can kind of do it that way if you know what I'm talking about. But otherwise, just do it u equals. And you don't have to do the u subs like I do them if you want it a different way. If you come from another universe, that is fine. So the derivative of 2 is 0. The derivative of -5x is -5 dx. And then solve for dx. Negative du over 5. And so we have sinh of u times negative du over 5. Factor out the negative 1/5. And then you have the integral of sinh of u du. And that's elementary. That's just Cosh u plus c. And then back sub. Okay. So negative 1/5 Cosh of 2 minus 5x plus c. Great. All right, let's. Oh, we could get so yeah. Up here, you know, we have all these basic integrals for free, and you would be wondering then again, what is the integral of hyperbolic tangent of x dx, right? We know the integral of hyperbolic secant squared x dx is just your hyperbolic tangent, but this guy we don't really know. But now we can sort of figure that out. Let's make it a little more difficult. Let's say hyperbolic tangent of 2x dx. So what do we do? If you had no clue, you could rewrite it as a quotient, right? So tanh is sinh over Cosh. And then you could do a u sub for the denominator. So du is sinh 2x times the derivative of 2x dx. So dx is du over 2 sinh 2x. Okay. So what do we have then? We have sinh of 2x all over u times du all over 2 sinh 2x dx. Sorry, my handwriting is pretty sloppy. Then you got a nice cancellation between the sinh, and you can factor out a 1/2 in this case, not a 2. U over u. And then it's ln, right? So it's 1/2 ln absolute value of u plus c, and then 1/2 ln absolute value of Cosh of 2x plus c. Oh, okay, I wouldn't expect you to have that one memorized, but any of these ones up here are fair game. So the simple ones, and then the related or associated integrals. So I expect you to have these memorized because they're just like the sine and cosine formulas for derivatives. And then if you have these memorized, you should automatically then have these basic integrals, with the exception of this one, this tanh. I wouldn't expect you to have it memorized, but I would expect you to be able to do this conversion and then a u sub. Okay. Okay, so that's enough of that. Let's move on. Let's see what section I'm on. 4. Okay, so section 5. I'm not as interested in this stuff. It really, at least in the classes that I teach, never comes up. But you never know in your engineering classes what's going to happen. I'm not an engineering person. I'm more of a math person. I wouldn't really call myself a math person, but if I had to choose between engineering and like pure math, I would say pure math. Okay. Okay. So in mathematics, there's pure math and then there's applied math. And in pure math, it's more like you're just kind of not doing any applications. You're just looking at the kind of the patterns and the overall kind of big picture kind of questions about math in general. And in applied, you're actually doing kind of how does this apply to an engineering problem, I guess. I don't even know that because I never took an applied class either. So, but anyways, yeah, math is divided into those two sections, applied versus pure. I would stay away from pure unless you want to become a teacher. Okay, so anyways, inverse hyperbolics, like I said, this is kind of, there's probably going to be 1 or 2 questions in the homework on them, but I'm not going to put it on tests. So not on tests. And I'll go on WebAssign and see what's going on there here in a bit. But I think it's important to kind of look at these. think about what a hyperbolic is. A hyperbolic is an exponential function. Right? So like Cosh of x is e to the x plus e to the negative x over 2, right? So what do you think what kind of function will describe its inverse? Well, if this is in terms of exponentials, I bet the inverse is going to be in terms of logarithms, right? And that turns out to be the truth. And we could literally go and solve for the expression for Cosh inverse. Okay? Let's do that real quick. You don't have to write this out. Okay, so how does that work? You interchange the y and the x variable, and there are restrictions on the domain to make it. If you look back at Cosh, when we originally drew it, it's not invertible because it doesn't pass the horizontal line test. So to make it invertible, you have to restrict the domain. So the domain will go from 0 to infinity. And if you look at the graph, you can see the picture pretty much tells you the range is from 1 to infinity. Okay, so there are some restrictions to worry about. Anyways, what do we have here? E to the y plus e to the negative y over 2. Multiply both sides by 2. 2x is e to the y plus e to the negative y. Set it equal to 0. E to the y minus 2x plus e to the negative y is 0. Multiply both sides by e to the y because we're trying to get a quadratic form out of it so we can solve for y. Okay, so if I distribute, I'll have e to the 2y, which is e to the y squared. E to the 2y is e to the y squared, like that. Okay, so then you have net minus 2x e to the y, and then plus just 1, right? Because again, you're adding the exponents. And then you could pretend this is a quadratic, right? So it's kind of like x squared minus 2x plus 1 equals 0, and you're solving for e to the y instead of x. Right? So e to the y will be negative b. So the b value, what is a, b, and c? A is 1. B is negative 2x in this case. So it's not quite an equivalence to the quadratic. And then c is equal to 1. Okay. Okay, so e to the y is going to be, e to the y will be negative b, so negative 2x, oops, it should be negative 2x, minus the square root of b squared, so it'll be 4x squared, minus 4 times 1 times 1, and that'll be all over 2 times a. Okay, so this will equal 2x minus, and we can factor out this 4, 2, and then this will be 2x minus 2 square root, and it's plus or minus, right? X squared minus 1 all over 2, and then we could butterfly it, and you end up with e to the y equals x plus or minus the square root of x squared minus 1. And then we can take the natural log on both sides, and you get y equals the natural log. And because of the restrictions, you can only have positives in natural logs, so it'll end up being x plus the square root of x squared minus 1. Okay? So yes, the inverse of a hyperbolic is a logarithmic expression. Okay. Okay. So, of course, then the book is going to ask you to integrate and differentiate these things. There's formulas in the book for these. Let's just look at one example. And then do one differentiation, one integration, and then I'll move into WebAssign. So the first one I want to show that the derivative of hyperbolic cosine inverse is equal to 1 all over the square root of x squared minus 1. Okay, so what you need to do is sort of go back to our definition in terms of logs. So really what we're doing is figuring out the derivative of this log. Okay, and so remember the derivative of the natural log is 1 over x. Okay, so this will be 1 all over the guts, x plus the square root of x squared minus 1 times the derivative of all that stuff, the x plus. So the derivative of that is 1 plus, and then we could look at the square root of x squared plus 1 as x squared, x squared minus 1 is x squared minus 1 to the 1/2, and do a power rule on it. So I bring down the 1/2, and I have x squared minus 1 to the 1/2 minus 1 is negative 1/2, and then the chain rule says times 2x. And then it's the laborious task of simplifying and then hopefully showing the derivative is as stated. So we have 1 plus 1/2 times 2x is just x. We could move that x squared minus 1 to the negative 1/2 to the denominator and change this into a square root. Inside these parentheses, and find a common denominator between the 1 and the x over square root x squared minus 1. Okay, so I'm multiplying top and bottom of the 1 over 1 by square root of x squared minus 1. Okay, and so what do I get? I get square root of x squared minus 1, combining the numerators over the new common denominator. And then you can see there's this nice cancellations. Goodbye, goodbye. And you have 1 all over the square root of x squared minus 1, which is what we wanted to show, right? Okay, great. Let's look at an integral. So again, there's formulas for the integrals in the book. The problem with these guys is that you use them so rarely that when you do see them, you're going to think that they're actually inverse trig derivative integrals, right? So this kind of looks like maybe an inverse tangent, maybe an inverse sine, right? But it's not. It's one of these nasty inverse hyperbolics. Okay. And again, the formulas for these are in the book. I'll give you this formula is du all over a squared minus u squared equals 1 all over 2a ln absolute value a plus u over a minus u plus c. Okay. So you want to get it into that form, doing maybe a u sub, identify the a value, and then plug and chug. Right? So if we rewrite the original integral, the a is going to be 3, the u is going to be 2x, right? And then you're going to have a 1/2 constant floating around. Let's actually do the u sub though. Okay, so you have the integral of 1 all over 3 squared minus u squared times dx, which is now du over 2. Factor out that new 1/2 constant that's floating around, and you get 1 all over 3 squared minus u squared du. So in this case, the a is 3, and plug and chug into that formula in the box. So I'll have 1/2 times 1 all over 2 times 3, which is 6, times the ln of the absolute value of 3 plus u all over 3 minus u, and then plus c, and then back sub, and you're done. Okay, so this will be 1/12 ln absolute value of 3 plus 2x all over 3 minus 2x, and then plus c. Okay, let's look at one of the exercises in WebAssign. finish processing. Thank you. Assign. They're trying to sign me out. They're really cracking down on signing people out of WebAssign this year. So that's probably their justification for raising their prices, right? Yeah, sorry. We want to look at this problem, whatever it is, number 4. You can use hyperbolics to model power cables. Okay, so sometimes you'll want later on when we get integral for figuring out arc length, we'll see these guys again because you'll want to know how much power cable you need to go from point A to point B or stuff like that. Anyways, let's take a look. So we have our model, y equals 9 plus 24 cosh of x over 24, and we're going from negative 24 to 24. Okay, they want you to graph it, and they give you some multiple choices here. So you can literally just evaluate this thing, at negative 24, at 0, and at 24, and probably get your answer. So this will be 9 plus 24 cosh. Negative 24 over 24 is going to be negative 1. I'm probably going to have to calculate that out, unfortunately. Okay. And then cosh of 0 is, if you remember, it's 1, right? So this will be 9 plus 24 is 33. So we should have 33 for the y-intercept. So, this one and these, you could tell which ones are not going to work, right? So this one's not going to work, and I don't know if you can see my cursor, and this one's not going to work because it's too low. So it's in between this one and this one, and you could it's pretty difficult to figure out which one it is, given that there's not very much information to go on. But it kind of looks like at negative 10, maybe it's at 35. So you could approximate, maybe we should figure out what it is at 10 and then use that as a guess, right? But even then, it kind of looks like they're both at 10. This is a crummy question. Maybe go to Desmos and just graph it. I have no idea what they were thinking when they made this. Well, let's figure out. Jeez, oh man. Let's figure this one out because I don't even want to bother with that. It's 24 times e to the negative 1, then plus e to the negative 1 is just e to the 1 over 2. So this will be 9 plus 12 times 1 over e plus e, and put that into our calculator somewhere. Probably Wolfram will plot it if you wanted to plot 9 plus 24 times cosh of x over 24. Let's see if it'll do that for us. It's going to be nice. Yeah. It's pretty uninformative if you ask me. But let's see what this is. Does it tell me what point that is? Not really. Well, you could plug in then negative 1 and 1 if you want. So you plug negative 1 in there and figure it out. 33. Okay, so y of negative 24 is 33, and of course y of 24 will also be 33. You put y of 10 in there. Whoops, I put negative 1. I meant negative 24, sorry. Sometimes. And now it's being a jerk. there it is. 46. Okay, not 33. This is 46. So it goes up pretty quickly, I think maybe is the moral of the story. Let's look at 10, putting 10 in there. I think it would have to take this long just to figure that out. It goes up to 35. So at 10 it should be around 35. You can kind of not tell, right? It looks like here at 10 it's above 35, so it has to be this one. Okay, so you just do a kind of a table of values, and you may have to guess, to be honest. All right, so anyways, let's look at the other questions. Part B. Find the heights of the cable at the tower. We kind of already done that, right? So at the towers, that's where the towers are negative 24 and 24, right? So you need to figure out the y of negative 24, which we already did, which is, you know, which is 46 point something, 46.03, and then that's the height of the towers, and then the midpoint height is y of 0, which is clearly just 33 if you plug 0 in there, right? And then find the slope of the model at the point where the cable meets the right-hand tower. So for slope, remember derivative is kind of the turbo version of slope, right? Derivatives are all about slope. So we need to get the derivative of that thing. So the model is 24 Cosh x over 24. So get the derivative. My prime is 24 sinh of x over 24 times the derivative of x over 24, which is 1 over 24. So that'll be sinh of x over 24. And then to get the slope at the right-hand tower, you just put in the right-hand endpoint. So y prime of 24, which we already figured out. No, we didn't. Sorry. Sinh of 1. And then we could use like Wolfram alpha to figure that out. .175. Let's make sure that's right. 1.175, yeah. Okay, great. Anything else? So there's some, you're going to need the formulas for derivatives. Maybe look at number 9. Y equals Cosh inverse of 8x. We saw above that the derivative of this thing, if y equals Cosh inverse of x, its derivative is 1 all over the square root of x squared minus 1. So in this case, using that formula, y prime is going to be 1 all over u squared. Okay, so if you have a more general definition of this, y equals Cosh inverse of u, y prime will be Cosh inverse of u times the derivative of u, right? So what do we have? Cosh, y prime is 1 over the square root of 8x squared minus 1 times the derivative of 8x, which is 8. So we get 8 all over the square root of 64x squared minus 1. Okay, I think we've beaten this to death. If you want to keep going, if you love these things, some people just love math, you can look up Tracics. The Tracic problems are pretty interesting. It's like the path a boat would make if you pulled it by a rope while you're standing on a dock. So you could imagine people in the Navy need to be concerned with this kind of problem. But okay, I think we'll leave it at that. And thanks for watching. Make sure you do the quiz on this one, and we'll see you next time.